Welcome back to the Foundry, ladies and gentlemen. This lecture, or the subject matter on this lecture, is going to be about risering. It'll be touching on directional solidification and a bit of mold manipulation as illustration for another part of this, the risering. And as is usual, I take full advantage of the photographs and the drawings that I can find on the internet so that I can illustrate the concepts I'm trying to pass on to you. The part of this, the beginning of this will be simple solidification, and then we'll cover a few of the other subjects. Now the very first picture that I'm going to be showing you, these drawings show the way the three simplest forms that atoms will form when all the heat has gone out of it, has been lost in the molten metal, and the metal solidifies. Given the fact that this is not a course in metallurgy, I will use simple cubic shape as my example of how atoms form dendrites. Now, this may be a new word for you, dendrites. Dendrites being the form that metallic crystals take when the molten metal cools and solidifies. They look very much like ferns one might see out in nature, out in a forest somewhere. Okay? So, the left-hand illustration of a simple cubic form will be used as an example. Now, once you start losing metal, or rather heat, in the molten metal, the repulsion, the atomic repulsion that is being felt by all the atoms in there, it gets weaker, and atomic attraction becomes stronger. As it gets cooler and cooler, the atoms start lining up into the cubic forms, and you will see something like this if you're able to look that closely. The atoms line up and start forming a long line, most more uniform than not, and eventually the center stem of a dendrite will be formed. Here, photographs have been taken to illustrate the manner in which the growth of dendrites progress from the relatively cold surface of the mold cavity towards the centerline of the casting, sucking in the molten metal to form the main stems of the crystals and the crossed branches. The individual crystals will continue to grow until it runs into a nearby crystal, or until all of the molten metal has been used. When all of the molten metal has been used, gaps between crystals may form, the size and shape of which depending on the metal used and the rate at which the crystals are solidified. Here we have another photo of the beginning of dendritic growth. When the main stems of a dendrite get long enough, the center of the main stem will have cooled enough so that atoms will attach themselves at that point to form a branch perpendicular to the stem. This photo is supposed to be what is seen using an electron microscope, and if you look at the main stem on the leftmost dendrite, you can see the cubic forms the atoms adopted and how they lined up to form the stem. Of course, they can't see the actual cubic form, but as you can see, it looks like a series of, like, for instance, if someone was making a pearl necklace, if they drilled holes in the pearls and started to put on the string, that looks a lot like those. If they were able to zoom in on those better, like maybe when the technology gets a little bit better, you would be able to see the actual atoms being lined up, but that's, I don't know if they have that set up yet. But those round little pearls are actually a cubic form that the atoms take, and they're lining up to make dendrites. This photo serves to illustrate how the dendrites, when done growing, can leave gaps between the crystals, preventing the casting to reach its maximum strength. Gaps like this can cause a valve or pump body to leak if steps are not taken to counter the defect. Now, directional solidification, in a very loose and fast and loose definition, is where regions of the casting most distant from the liquid metal supply, that is, you want that to freeze first, and for solidification to progress from these remote regions towards the risers. In order for you to feed a casting, you're going to have to put a riser on the thick parts. And if you're an experienced molder, you can judge the best places to put the gating system so that you can feed the risers. Risers being a reservoir of molten metal. You can feed the risers the very last thing in the entire pour, so that everything else is cooling down while the riser is still plenty hot. Now this picture is showing I wasn't quite sure what they're making here. Now, it could have been that they're making a flywheel for a small steam engine, as is illustrated here, or a belt, a wheel to put the big flat leather belts on that you can see here, that would run some machine. Back in the old days, they used to use water wheels where there was a source of water as a power source. Attached to the water wheel would be a long shaft, and on this long shaft would be wheels like you can see up above this guy. Periodically and directly underneath the wheel would be a machine that has a corresponding flat wheel that you put those what looks like rubber bands up there. They're not rubber bands at all. What they are, they're flat leather belts that takes the movement of the water wheel on that flat wheel up there, transfers it down to the machine, and you can perform work by using that. Now back to this casting. Now the casting looks pretty good. I don't see anything that's facing us that looks bad, but look how they fed it. They poured the metal, and this is aluminum. They poured the metal down something you could practically put 2 or 3 fingers in, and even though they did have kind of a splash basin underneath that takes some of the turbulence to absorb some of the turbulence from that pour, that metal was poured directly into the mold cavity. Everything, including loose sand and the dross formed by all that turbulence that they were making, went directly into that mold cavity. And who knows where it is. It might have been right there where the in-gate was attached. It might have just stayed right there, or it might have been pushed throughout the casting, rather the mold cavity, and got lodged into the skin of that casting, which that's a casting defect. It's no longer at those points where you have the dross. At those points, that's not solid metal anymore. It's closer to being rust than it is to being solid metal. Now, dross. I've used that word several times. For those of you who've never heard that word before, what you have when you pour metal, if you don't take real good care of keeping turbulence to a minimum when you pour it, because you're never going to erase every little bit of turbulence. It's going from a crucible, falling through the air, through a mold, and hitting the bottom of the sprue. You're going to get at least a little bit of turbulence, and you're going to be manufacturing some dross. Dross being a combination of the metal that you're pouring and oxygen. That, you know, when you splash it around like that, the oxygen attaches itself to that metal, combines with it, and you wind up having something that kind of looks like a metallic oatmeal or a metallic mess of fiberglass kind of thing. You know, it doesn't look great. You can kind of get an idea of what it might look like if you look very closely at the bottom of the sprue where the splash basin is. All that, you know, it's not smooth like above the splash basin. It's all kind of messed up with holes and pits and all that in there. That's a good indication that right there is a bunch of dross that was formed. And because that sprue wasn't tapered at all, you know that gating system that they have there was never pressurized. So every moment that they were pouring that, they were manufacturing dross. You know, as soon as you pressurize your gating system, and this is a subject matter I'll be covering in another video. Every moment that, as soon as you pressurize your gating system, you stop making dross. Okay, it's very important to get that system, you know, dug into the sand so that you can pressurize it. Never mind talking about that now. That's for another lecture. That'll be a whole lecture. Heck, who knows? That might be almost as long as the lecture I did on sands. Anyway, so risers. Here you have a casting. The outer wall, the ring out there is uniform. The spokes going in towards the center is uniform. But something that's not quite the same as everything else is that central hub where the shaft would go through. Now it's obvious that you know, if you have a thicker part in amongst a bunch of uniform parts, that part is going to be the part that shrinks. And they put an open riser on top of that to feed that. Now that riser wasn't, you know, the right size. It was too small. And you can see that, but it did do at least portion of its job. See how it's got the dip in the very top. That's called piping. That's got a dip in the top of that riser where that portion collapsed as it was feeding everything down below. So, if you were to take, now to illustrate what might happen even in a uniform casting, if you were to cut off that excess metal, you know, the sprue and the ingate, cut that away, take all those spokes out and the central hub out, you just have the ring. Now imagine that you've taken a bandsaw and you've cut a single cut somewhere in that ring, all right? And then somehow you magically flatten that ring out to where it was in the shape of a slab, all right? You would then have something like this. Now, that's got a kind of a split down the length of it that I've put in. So what you're doing is you're going to take another bandsaw or a horizontal cutoff saw, and you're going to cut straight through the middle of that slab. Now what you're looking at in the middle there, well, almost like a star shaped, you're looking at the gap that would be formed if you weren't feeding that. All right, if you don't overheat your metal, you pour it at a good pouring temperature, the skin, all the skin that, you know, that represents the mold cavity will solidify first, and the molten metal inside that skin will feed the thickening of that skin until it absolutely, it just solidifies all the way down to the very center of that mass. It's going to run out. unless you have a riser attached to it to give it some more molten metal, it's going to run out. And along the length of this slab and in the center is going to be some shrinkage. And here's a picture that shows that type of shrinkage. On the right hand side of the picture you can see, well, it's not, nobody took this and polished it down to where you could see the individual crystals. You can see where they cut straight through it, and you can see the saw marks. But if you look and ignore those saw marks, you can see where the crystals grew and how it went from the right hand side to the left hand side. And at the bottom of the picture, you can see how dendrites were growing straight up. So this would be a good good illustration of what you would have even in a uniformly thick part of your casting. It may not show on the outside, but it's going to be there. But does it or does it not have anything to do with the actual functioning of the piece you're making? Probably not. This wheel that they're making might last 100 years without any extraordinary damage being done to it. Even if it fell or something, it'd probably still last pretty good. But keep in mind that not everything is just a wheel. You might be making a valve. You might be making a pump body. Things that are going to have pressure show up inside, or rather pressure generated inside that casting. And if you've got voids like this inside the wall of your casting, well, it's going to be when you get that tested and the casting starts springing a leak, it's going to be rejected, and you're going to have to make that thing all over again. So when you're making something, keep that in mind. If it's going to be pressurized, put risers somewhere in there, and gate into the risers, so the risers will have the hottest metal when you're done pouring, so that you won't have any of these gaps, even in uniformly thick casting walls. This next picture shows two of the three main riser types that you'll see if you ever use any. The one on the left is called a blind riser. Now, the reason why it's called a blind riser is because it's not open to the atmosphere. It's like somebody threw sand in your face and now you're blinded. And nobody can see it. All right, so it's called a blind riser. Now, that's not the shape I would normally see, because that looks like they're trying to make that solidify, whereas that's, in a direction from the topmost surface of the riser down to where the ingate is. But you don't want that thing to solidify quickly. You want that to stay molten as long as it possibly can. So I really don't get that shape, unless somebody was just accentuating, or rather exaggerating, that shape because of the drawing they were doing. The right hand side mold cavity is being fed, or going to be fed, by an open riser. Okay, it's open to the atmosphere, and that one would, the draft on that, or the angles that is being shown on that riser, that's a good idea, because when you have part of your riser exposed to the atmosphere, that heat is just running away, and so that will start to solidify quickly. And if you have it thick up there, you've got extra metal that will continue to feed that casting down below as it's solidifying. Now, this next one is kind of a specialized one, not this next one, but this one that's next I'm going to be showing you is a example of a blind riser. Now, the rightmost one, you make a blind riser by making that basic form right there, where the bottom is a little bit bigger than the top, so that you can pull it out of the sand easily. But the after you make that, you've got to cut a wedge or a notch in the top. And well, what that does, it allows the permeability in the sand to give you some atmospheric pressure on the top of that, so that there's no vacuum being formed as it's trying to feed whatever it's touching. And if you formed a vacuum in there, it might be a little bit hard for that metal to be drawn into the mold cavity, as the mold cavity is solidifying and it needs to be fed. So if you add some a cracker core, they call that, or a green sand core that allows the permeability of the sand to give, provide atmospheric pressure, there won't be anything to prevent it from doing its job easily. Now the next one is a drawing of a blind riser. In this case, the blind riser is close to the casting, to the side, and will still feed it very well. I don't like how small the contact area is there, because that contact area, the neck right there in the middle of this, is small enough that might freeze up before the casting is fully fed, and before the molten metal in the riser has solidified. It's not going to feed that casting. But this also just might be somebody's idea of making an illustration. In the real world, I would have a lot more of that mold cavity opened up. A channel opened up to feed from the riser into the casting. And here's I made this little drawing here to illustrate what's called a wedge riser. Many times you'll have to feed a casting that's got a large flange on it, like the end of a pump body, or a pipe, where you have flanges on a pipe that you're casting for some reason. Well, that's the portion of the casting that's going to shrink, because it's almost always considerably bigger than the rest of the pump body, the wall of the pump body. And if you don't put a riser on that and gate into the riser, the top of that flange is going to be collapsed. Something like what you saw on that wheel, that one riser that was feeding the center hub of that wheel. Well, that'll happen in the flange, and if that happens, that means the strength and the shape of that flange will be affected. So you got to feed those, either by using a wedge riser like this, or by providing a riser on the side. Now as long as it's filled in, it'll be providing metal. It'll be a reservoir of metal, and that flange can solidify. And instead of having the solidification end on the top of the flange, the directional solidification will have been pointed towards the side of the flange, and that riser will still be feeding the flange. Looking at this, it looks like they did a good job on feeding it, but they still didn't make a good gating system, because even though the sprue looks like it's a little bit tapered, and they made a nice pouring basin, down in the bottom underneath the sprue they don't have a splash basin. Underneath the riser, that basin, they should have had something that looked like that at the bottom of the sprue, so that whatever amount of dross that they manufactured when they poured down that sprue, that would have been mitigated. The effect would have been mitigated by that splash basin, and less dross would have been fed. In addition, they don't have a place for that dross to go other than directly into the mold cavity, somewhere in there, unless it got shifted up no, it wouldn't have done it, because the riser is the last thing you get fed. So that dross went into the mold cavity. And somewhere in there, I mean, that's obviously going to be something that's going to have pressure on the inside. I'd be worried about the integrity of that pressurized vessel. But for the, you know, for this lecture, it's just showing a way that you can feed a flange with a open riser, and it could have been a blind riser there too, as long as the blind riser was big enough. This is, you'll either have a wedge riser or you can have a riser put on the side. Wedge riser is a little bit harder to work with because you would have to saw off as much as you can with a either a hacksaw or a cut-off saw. Excuse me. And then you'd have to put that casting inside of in a lathe and form that lip by machining it, which would be that imagine how much easier it would be just to take and cut off the riser that you're looking at now, and just grind a little bit with a grinder, a handheld grinder, and it would be ready to go. You just send it to the machine shop for them to do their job. This picture illustrates what's called piping in the riser. Now, because of the shape of that riser, I would say that those are blind risers. Okay, the bottom half is a portion, what it might appear to be a portion of a casting that they were trying to feed by using that blind riser. So, and the what looks like a line that's in between the riser and the casting below, that might have been a parting line, because the geometry of the blind riser, you wouldn't be able to wrap it and pull it straight up. You would fight all the rest of it because of that draft there. It wouldn't permit it. So once you take the top half of the cope off of the drag, in this case, you'd be able to turn the cope over, wrap the blind risers, and pull the pattern for the blind risers out of the sand. So those have got to be blind risers feeding the casting down below, and they're just illustrating how much the risers actually fed the casting. Now the casting on the right hand side, it looks like it was well fed. Despite that neck right there, in there, I wouldn't have had that neck there, but they must have put that there for, I don't know, for ease in removing the riser, or maybe that's some kind of a platform or a boss that they had to have as part of the casting. A good contact with the riser is absolutely essential, and there's no use in having a large contact if you have a tiny neck. Now, another thing I can see is that these must have been two different castings, because the one on the right is good, but the one on the left shows something of a defect. See that brown smudge, what appears to be a smudge in the casting, the bottom of the casting, or rather the casting portion below the riser? That is not solid metal. If they were to be able to zoom in on that, they will have cut into a portion of it that didn't solidify, or rather didn't get fed by the riser and solidify before that neck choked off the metal and froze. If you were able to look really closely at that brown smudge, you'd be able to see the edges of crystals, where the crystals grew until they ran out of metal, and then you had that gap I showed you earlier. It would be almost like the inside of a geode, one of the semi-precious stones that you can find that has agate formed inside of it. That would look like that inside that. But why do they call that piping? Well, when at the time that they coined that phrase, most everybody would have known what somebody was talking about if they were talking about a defect called piping, because everybody who was anybody had pipes back then in the 1700s and 1600s and 1800s. There was there was as many clay pipes around as there is pieces of plastic nowadays. And there's piles and piles and piles of pipes that accidentally got broken, that the archaeologists have found. And this is the the bottoms. You can see the bottom where the stems broke off. That was mainly what happened. Is your stems would break off and they'd have to throw that pipe away. But if you were to look, be able to take that bowl, the part where they put the tobacco, and cut it in half, you would see something like this. Now, see inside the bowl, or what they call the pot in this illustration, that looks exactly like the piping in those risers. Hence the reason why they call it piping, because it very much looked like the bowl of a pipe. And here is a casting. I am not exactly sure what the use of that casting would be, whether that would be a symbol of some sort in a religious setting, or I can't remember if that would be a symbol of a male or a female. There's symbols for male and female, but whatever the case might have been, this is obviously aluminum, okay, and as rough as the edges were around there, it was obviously made in a green sand, like the bentonite type of sand, with clay bonded sand, I should say, clay bonded sand. And we're looking at the bottom of the casting. Now, the bottom of the casting typically is the best part of it, because all the molten metal that's in there, even if you have dross inside the molten metal is going to be denser and heavier than the anything else in there. Well, it might not be denser and heavier than sand, if you were foolish enough to have a dirty mold before you closed it, and left some sand particles all through your mold cavity. Now that might stick to the mold wall in the bottom, but if let's say that's not a case and all you have is dross and good metal, well, the good metal will settle to the bottom, displacing the lighter dross metal, and the dross will generally float to the surface and stick to the mold cavity that's represents the surface. The top half of the mold cavity. Here we have a very good example of what might happen if you overheat your metal way too much. Now look how thick that casting is. That casting, the molten metal did not need to be any hotter than 1250 degrees. But I'd venture to say that whoever poured that, that thing must have been 1400, 1500 degrees for that shrinkage to take place like that. Especially it took place in the bottom of the mold, on the bottom facing of the mold cavity. I've never seen anything that bad like that. Now, if that was the top portion of the mold, I've seen that, because usually when you pour the metal into the mold cavity and it all fills up, the stuff in the very bottom will have started to solidify before you even fill the mold cavity completely. And usually the very first surface that solidifies becomes the strongest and thickest at the time that everything's solidifying, and normally that would stay nice and flat. But this was so bad that the metal was too hot, and everything started to pull away as things solidified. Anyway, in addition, as you can see, in between, where they introduced the metal, it went directly into the mold cavity. There wasn't any runners. All they had was a huge down sprue, which apparently I'm thinking that what they meant was that they were going to use a riser as both the sprue and the riser. And when you do that, you have something so big that nothing can ever get pressurized. So every moment that they were pouring that metal, that superheated metal, they manufactured dross. That would have been thrown away. But that's not even the right way to pour that. I made an illustration just below on the way that I would have poured it myself. Okay? If you had your down sprue, now we're looking at it from the bottom like we're looking at the picture from the bottom of that casting. If you were to put a riser on the very end of that cross-shaped portion and you put the ingate directly into the riser, if you made a runner that when it left the splash basin and you left about an inch or an inch and a half of runner past the ingate, any pardon me, any of the dross that you might have manufactured when you poured the metal would have been pushed past the ingate before the runner would have filled up and allowed the metal to enter the ingate, and then the metal would have gone straight down the channel that is represented by the mold cavity. When you pull that pattern, would have gone straight down that channel all the way to the circular portion of that mold cavity, filled that up, and the very last thing that would have been filled up would have been the riser. That would have been a perfect way to feed and support the solidification of that casting, the directional solidification of that casting. Now, why would it had solidified at the circular portion first and not anywhere else? Well, because when that casting fills up totally, well, what do you have? You have that entire outer wall in contact with sand, and you have an inner wall that's in contact with sand, which hurries up the solidification of that metal. As you go up in the cross-shaped part of that, you only have the outside shape, the perimeter of that mold cavity is touching the sand. So basically what you have is a chill in the middle of the round portion. A chill being something that helps solidification along, and making a certain portion of your casting solidify faster than it normally would have been if you hadn't put that chilling material in contact with the mold wall. All right, so you see on top a bad case scenario where they put a down sprue that was going to be their riser. They made a bunch of dross which dumped directly into their mold cavity, and they poured it so hot that you had even the base, the bottom portion of the casting shrink. So you have the good and the bad right there. The good being on the bottom, and if that was my project, I would have had it to where it was just about 1250. The pouring range on aluminum, well, as stated in the Navy's manuals and all that, and it worked very good for me for 20 years. Aluminum, the pouring temperature is 1250 degrees Fahrenheit up to 1400 degrees Fahrenheit, and if you go beyond that, you're going to get what you have illustrated in the photo above. Now the next one it illustrates directional solidification and how things would be affected if you put a a riser at the end. Basically, all you've got is kind of a slab that somebody's rammed up and formed, and all the way on the top half they're showing how the top wall, the end wall, and the bottom wall all come together at the very end of that slab, and then slowly feed from the right to the left until the casting is almost finished being fed, and you still have molten metal in the riser. Then that riser, if it wants to, you can have piping in that riser. You don't want piping in your casting. It doesn't matter if you have piping in the riser, because that riser is going to get cut off and used in a future project. Now, this next picture is an example of mold manipulation. You want to affect the directional solidification of this casting. If you were just to feed this casting, with the casting being absolutely flat, the odds would be very good is that the bottom would start solidifying before the top, and the then the ends would finally, the top would finally start solidifying, the end would solidify. You would have what we just looked at. But apparently maybe this casting might have had some problems doing it that way. So they decided that it would be better to force the issue to make absolutely certain that the very end of the casting solidified quickly, and directional solidification was established. About before. All right, we have a casting that basically looks like a slab that somebody wants to make absolutely certain that is going to be fed to, fed from the far end of the casting over by the vent hole, and will fill up until it reaches the riser. And at that point, you could just set it flat, because you've already done what you intended. You've already started the solidification process at the far end of the casting, but it doesn't show that here. But it's a good way to absolutely make certain of your directional solidification by way of mold manipulation. Now, I've seen several different types of mold manipulation. I've seen one type of mold manipulation where they did almost everything that they normally did. They poured it and all that stuff, and then put a plug inside the sprue and flipped it over 180 degrees, and somehow, I think it was at that point, they were trying to make what used to be in the cope the drag, and have that casting solidify there quicker than before. I don't know. It was a long time ago since I've seen that. It made sense at the time. I said, oh yeah, that would have worked. But I just don't remember the particulars. Now, if you look close, the top picture shows, I put the names, in there of what each portion of that mold cavity is. The bottom, where it says horn gate, now you may never have heard about the horn gate. Okay, it's an ingate that feeds metal into a casting or mold cavity, but it's in the shape of a horn, where you have one end is going to be narrower than the other end, and once you ram it up into your mold, you can wrap it, and then slowly slowly pull it out of the mold. You're going to get the thick end. You put a nail in there, you wrap it, and then you slowly pull it out and turn it at the same time, so that the shape of the horn won't scratch up the inside of that cavity you're forming. All right, there's specific reasons that you use a horn gate. Most of the time you wouldn't want to use a horn gate, but in some cases a horn gate comes in very handy. And in this portion, the horn gate is coming in handy, because it's trying to feed the bottom of the casting to where it fills all the way up. Then once it fills all the way up, to the point where it's even with the bottom of, or rather the horn gate. It's even with the horn gate. Then the end gate that they manufactured is going to be feeding directly into the riser, so that that's where your hottest metal will be. And obviously, because it's not open to the atmosphere, that's a blind riser. Okay, it's an excellent example of both mold manipulation and directional solidification. This next picture, kind of hard to see, but the reason why I added that is I wanted to show how one way that a horn gate can be used. Now the right hand side of this picture shows a huge sprue, down sprue. Somebody's fist could fit into that, it looks like. So it was making 100 pounds of dross as it was being poured. But once it became poured and that area started to fill up, it ran into the horn gate. The horn gate directed it to the bottom of the riser and fed the mold cavity, filled up the mold cavity, and then once the mold cavity was full, the way the horn gate was pointed towards the riser, it would fill the riser last, giving you the hottest metal in the riser to feed that casting. That's a good idea, but the in-gates, the down sprue and the splash base, and then all of the rest of that was very poorly done. Here we have what is a good example of where you would how you might feed a hand wheel. Now this hand wheel shows it's basically flat. Okay, it's got the outside ring that you can grip. You got your spokes that are going towards the central hub, where you would drill and maybe tap it, or just drill it and put it on a machine, and you can utilize it that way. And it shows also that the outside ring is basically, with the exception of where the handle would have been drilled and put in, it's pretty uniform. The spokes are very uniform, but the central hub is quite a bit thicker than anything else. And you would fill that. You would put the riser on that. All right, to feed that central hub. The rest of it would solidify pretty quickly, and that central hub might even feed the rest of it before it solidifies and draws the molten metal from the riser. This is the way I would the drawing that you have below is the way I would feed that. All right. You have your splash basin that mitigates the amount of dross that you'd be forming as you pour this. The runners would push the metal, or rather the dross, to the end of that runner and then fill up the rest of the way, allowing the metal to start entering the ingates, which would start filling up metal inside the mold cavity. And then finally because it's the ingate is feeding directly into the spoke, it would feed everything first, and the metal would still be moving inside that spoke, would still be hot, so that those two spokes wouldn't solidify until the metal stopped, and the metal wouldn't stop until that riser was done. After the metal stopped, those spokes would solidify, and the bottom of that central hub would start to solidify, and that riser, staying, because it was the last bit of it that was the hottest metal, would solidify last, feeding that central hub. Okay, now that's your basic hand wheel. Here's another type of a hand wheel. See how it's been inset? It's a little bit hard to ram up, You might have to do a few different techniques, like drill a hole in your bottom board and ram it up that way, the central hub being inset into the bottom board, and then ram it up that way. Or you could just put the ring flat against the mold up board and then ram it up that way. And then you would, what you'd be doing is you'd be making your cope first, ramming your drag second, and then flipping the whole thing. You would take it apart then, and you would cut the riser, and the way you would pour it is the way it's set up in the drawing below that hand wheel. Here's a good example of how you'd use the horn gate. Now, see, you get the sprue. The sprue is tapered, so it would become pressurized. Minimalizing the amount of dross being formed. The little bit of dross that's formed is pushed in this horn gate that's going into the central hub. The metal would rise. The dross would stay on the surface of the metal. As the metal rose inside that central hub, it would enter the cavities formed by the spokes, and those spokes would feed the outer ring. And then when that backed up, the metal would then be pushed straight up into the riser, and that riser would be the last place and that would be filled, and where the metal would be the hottest. Because the hub in the middle there would be smaller, it would automatically start to solidify before the riser ever did. And then once it became solid, you would still have some molten metal in the riser, and it would start solidifying. And then on the very top of the riser, whether this be a blind riser or a riser open to the atmosphere, the piping would take place, something that that you expect. This next picture are examples of what happens when either you don't put a riser on a casting, or you design it incorrectly. All right, the right hand side may not have even had a riser, I'm not sure, but if it didn't have a riser, that's the reason why that shrinkage that took place inside in the middle of the metal. Now notice how it was about the middle of the metal, that the wall cavity, or rather the walls of that casting, did solidify, and as the walls solidified and drew molten metal into the crystals, and everything progressed towards the center line, this is what happened. This is the shrink that took place after all the metal had been used. And you had this is a big void left over. Now on the left hand side, it shows where the riser, which apparently was an open riser, it was fairly large, except that look at the neck where it joins the casting. It's nowhere near the width of the casting, and nowhere near the width of the riser. So apparently that froze up and didn't allow the final solidification of the casting to take place before that froze up. And the reason why I know that is because, I mean, if you were to have that casting on the bottom is solid metal, and then you only saw the piping and stuff up above inside the body of the riser, that would be that would be a good example of why you needed a riser and how the riser should have been designed. The problem here is that the neck was narrow enough where it restricted the flow of the molten metal, froze up, and then the molten metal that was left over inside the casting was used up, and you had your gap being formed inside there, and then the molten metal inside the riser was used up, and the it looks like the piping almost went all the way to the bottom or to the base of the riser. So that riser should have been, at least almost all the way to the edge of the casting, if not past the edge of the top of the casting right there, to feed it properly. Usually the only time that anybody ever makes this kind of mistake is that they're worried the amount of time it's going to take for them to remove the riser, and then be able to machine the casting. Now, back in the 1940s, or actually in 1940, some mathematician came up with a formula that would help you as a molder design, or even the person who might have been the manager design the size and the size of a riser. Okay, it's general knowledge that the best shape of a riser is a cylindrical shape. Okay, for obvious reasons, you would be drawing too much molten metal into the riser itself if it was any other shape. So a cylindrical riser needs to be used, but how do you determine whether or not, how big is the riser going to be? How do you design the riser? Well, this one mathematician made up Chvorinov's rule. Okay, here this paper here shows you the portions of Chvorinov's rule, but this Chvorinov's rule didn't include every casting that was out there. It basically just helped you with castings that were kind of what they call chunky. Okay, basic shapes, not too big, certainly not long, ranging kind of castings. The person after that tried to build on Chvorinov's rule. This guy named Kane made up an equation that kind of filled in the gap, and he made it to supply the size of a riser that you needed to pour or to feed a rangy or a lanky type of a casting, something that might be fairly long. Okay, but they found out that these two equations were way too sophisticated for the molders and even some of the engineers of the day. It was too sophisticated, too much work to do the job. So as a result of investigations for 2 decades leading up to about 1952, the two methods discussed previously are no longer necessary. Now the proper riser dimension can easily be attained through this simple shape factor. Now you have a shape factor where you take the length of the casting, you add the width of the casting, and you divide it by the thickness of the casting. When you get that factor, you would go to a chart, and using that factor would be on one leg of the chart. The other leg of the chart, you had what was labeled R sub V divided by C sub V. Okay, where R sub V is the riser volume and C sub V is the casting volume. Now that's a little bit simpler than the other two formulas. Okay, but you'd have to find out what the casting volume is, so that you can find out what the riser volume is. All right, just use your math, your math that you learned, and when you're able to when using your algebra, when you're able to have everything on one side of the equation and all you have is your riser volume on the one side, you can figure that part out. Now, one of the ways that you can use to find out casting volume is you take a container that the casting can fit in fully, fill that container up with water to where it's just almost overflowing. Set up a way that where you can catch water into another container, and then slowly lower that casting into the larger container. When you have every bit of the moisture, or rather the water that overflows that first container is caught, and you measure it, you'll find out how many cubic inches that might be, or how many cubic feet that might be, and there is your casting volume. Okay? Even then, these are, that's a lot of work just to try and design a riser. All right? Well, Navy came up with a really nice, a simple way to do it. Okay? And I will read it. The following is taken directly from the Molder 3 and 2, which was our study book and our basic reference book whenever we had any questions. To determine the diameter of a riser, where it contacts the casting section, draw a cross-sectional view of the section. For instance, you take a measurement of the thickness, you take a measurement of the height and the width, and it's it's almost like you're having somebody saw through that drawing and showing you the cross section of it. All right. Now you inscribe within the cross section the largest possible circle. Measure the diameter of the inscribed circle and multiply it by 1.5 to obtain the diameter of the riser. So if you had a cross section that you're trying to feed that was an inch in diameter, or rather the inscribed circle was an inch diameter, the base of your riser is going to be 1.5 inches. Okay? The riser should widen to a slightly greater diameter above this point of contact or neck. Okay? So that it kind of takes up on any shrinkage, any solidification that might take place inside the riser. You don't want that to solidify quickly and slow down its capability of feeding the casting like you saw before in that aluminum casting. All right. One technique that you can use to make certain that your riser has the hottest metal, if it's open to the atmosphere and you're pouring your casting, as soon as somebody or you see that the metal is starting to come up into the riser, stop pouring, go directly to the mouth of the riser and pour directly into the riser. All right, you will absolutely have the hottest metal in that riser, and no matter what's happening elsewhere, that riser will stay hotter than the rest of your casting and will feed your casting. Now we know how to make the diameter of the riser. It says here a height of 1.5 times the diameter of the riser should give maximum effectiveness to the riser. To summarize, find out what your cross-sectional thickness is, make the diameter of the riser 1.5 times that, make the height of the riser at least 1.5 times that, and you'll have the size of the riser you need. Now, the Molder 3 and 2 also says don't make it any taller than it needs to be, because you'd be utilizing more metal than you have to. But if you're going to be cutting the riser off anyway and reusing it later, that kind of that argument's a moot point. All right. So remember, you have to have risers where there isn't a casting that's all totally uniform thickness. And even if the uniform thickness, you have a casting you're making that has uniform thickness, it's a good idea to put a riser on the outside edge of that so that you won't have anything in the middle solidifying. All right, I hope you've learned something, and for you molders out there, Liberty Call.